In this video, we'll do some reduction with laws. So, the first question, we want to use laws to reduce not P and Q arrow R. So the first thing we'll do is we'll use the definition of the conditional to change P and Q arrow R into not P and Q or R. So remember, we have P arrow Q. This is the same thing as not P or Q. So those are equivalent. That's what we did in the first step. Second step, we'll use De Morgan's law and we'll distribute the negation inside of the brackets. So we're going to get not P and Q. And remember, we flip the or to an and we distribute the negation. So not R. So it's not P and Q and not R. And that is by De Morgan's. I guess I'll label this. This is the definition. Okay. Then for the third step, we'll do double negation on the not P and Q. So we get P and Q and not R. And that's just double negation. Okay, so that looks like it's as far as it can go down. So instead of writing not P and Q arrow R, we could just write P and Q and not R. So that was a pretty quick one. Second question. Let's prove that not P or Q and P and Q is the same thing as just P and Q. So we'll take one of these and reduce them to the other. So let's start off with this one. So the first thing I want to do is I want to reduce this part here because we have P and Q. So P and P is redundant. So we can change this to not P or Q and P and Q. So I think this is the identity law. I think that's the name I used for it. Normally I should really do some changing of association here. I should group the P and P together first, but I just skipped that step because really it's unnecessary. I don't actually need these brackets here. Okay, so now we have not P or Q and P and Q. So what's the next step here? Well, we could distribute these. So let's take a look at this next step here. We can distribute P and Q into Q, and we can distribute P and Q into not P. So we have P and Q, and this becomes and Q, or P and Q and not P. Okay, so that was the distribution rule. If you don't remember that, if we have P and R or S, this is the same thing as P and R or P and S. And we just did that with P and Q being our P, and then this is our R and our S. So it looks a little bit different because we have this P and Q there, but we've just used it as one term here, as one statement. Okay, now we can do some more reduction. So just like we did in the first step, we can turn this P and Q into P and Q, or P and Q and not P. And that's the identity again. And then, of course, for our last step, we see that we have a P here and we have a not P, and these are all conjunctions. So this is really saying P and not P, and we know that's always false. So that's saying P and Q or false, because we cannot ever have P and not P. So I don't know what I want to call this. Maybe we call this a negation law. I totally forget what I used for it in the previous video, so just use negation. And then step 5, we have P and Q or false, and we know this simplifies to just P and Q. And because if we have something that could be true or something that's always false, it always is going to take the upper value. So that's always going to take the upper value of P and Q. So that's the second question. We have successfully reduced this thing on the left to this thing on the right. Okay, and then our third question, we want to show that P or Q, arrow Q, is a tautology, which means we want this to reduce to true. That's the same thing. Okay, so our first step, we're going to use the definition of the arrow to change this. So we'll get not P or Q or Q arrow Q. And that's, of course, the definition of the arrow. For the second step, we're going to do the same thing with this arrow. So we'll have not P or Q or not Q or Q. Okay, so once again, that's the definition of the arrow. Here we see not Q or Q. So this is always going to be true, because this is the law of the excluded middle. So in the end, we're going to have not P or Q or true. I'll just call it law of the excluded middle. And then for 4 here, if we have something or true, remember it's always going to take the upper value with the or, and true is always true, therefore the final statement is true. So we have proven that P or Q, arrow Q, is a tautology. And why is that? Well, let's think about this for a sec. You don't even need laws to justify this. If we have a statement that is true, so P arrow Q, and we say, look, this is always a true, this is always 1, then that means that this conditional will always be a 1 as well. And we know this is a 1 because if we have Q arrow Q, this is always true. So if we have something pointing to this, it can be whatever it wants in the world, and this will always be a tautology, because this is always a 1 over here, which means that this arrow will also always be a 1. Okay, so that was the practice problems for logic laws. So if you have any questions about these, leave them in the comments below, and I'll hope to see you in the next video.